or the best way. So here, relative to the coordinate system here, you can define the angle here that way. And you can actually compute not only the x and y changes, but the theta changes too. And that's why the photo will look like it's following your fingers. And it doesn't need, you don't need anything more than sines and cosines actually. Like that's all you really need after that. And then after that, you start getting to linear algebra and then college stuff.
Are you with him, Cody, or you?
Yeah, I understand. I mean, because it's basic things that we're learning in, pre-calculus.
Yeah.
We went over sum of difference equations. We went over the actual trig identities. And, is there any way that can relate to, I guess, if you're moving, I guess, in the diagonal, would that be considered like a tangent maybe?
Yeah. So a lot of this is
Cody,
and I guess in a negative direction or in a small direction, I guess.
Well, the really beautiful thing is, no matter if it's positive or negative, this equation works. And the similar things about the angle stuff, it almost works for pretty much any numbers you put in there. So even though it looks like, what if I moved it this way, it actually still works out exactly the same math. That's what the cool thing is. It's all generalized so that no matter where your fingers are, the math, the equations are pulled, and you just run the equations, and it should all work. I gotta think of a better way to explain this stuff. Yeah, let's go back to root. So let's say I have a box here, and let's call this A, B, C. And the box is, we have a unit box here, and it's just, and we want to count the box as angle. If theta equals 0, then it's kind of flat this way. But if we drew another box where something was like this, it would be like that, right? So so if we had our finger at B and we actually moved my finger here, you kind of think the box should do something like that, right? So we literally then have to find the angle here, and that's possible because we know what B prime is, and we know the x and y components here and the x and y components here. And again, this actually turns out to be exactly where you do the trig.
So with this, so this is about. If this is the box, then would this be the actual curve?
Yeah, exactly. So this would, let's say I follow this curve with my finger here, and all along the time I'm basically computing new theta values that actually tell the box to rotate, so that B always follows my finger. And the way that's possible is literally just by looking at sine and cosine here. This is literally the B coordinate lets me define theta, and you can do it as arctan. You can literally do it as arctan, right? Tan rex, right? That's literally will give you the theta. And then you tell the computer to draw the box at that theta. Yeah, so this is simple when you're not moving at the same time, you only want to rotate it. And then it turns out that rotation and what they call translation or movement is completely independent. So you can actually have the separate equations for x plus delta x and y plus delta y, and then you can still hold it that way. And then you can start taking this 3 dimensions and even higher dimensions. Actually, all pretty much works out the same way.